Hi, everybody. Here we are at Hogwarts, and I just wanted to do a couple of the problems, a couple of the examples on 1.1. So here we go. Let's share my screen, and we are good to go. Okay. So this was, let me just show you what we're talking about here. There's a problem up here that if you add the odd numbers, 1, 3, 5, 7, dot, 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 you get a perfect square and squared. So let's check it out. So first I'm going to prove it, then I'm going to show on a spreadsheet just to demonstrate how it actually works, or that it actually works. So let's do this. Let's prove it. And okay, so 1 plus 3 plus 5 plus dot 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 plus 2n minus 1 equals n squared. So step 1, you have 1 equals 1 squared. So now I assume that this is true for some value of n. So 1 plus 3 plus 5 dot 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 up to 2n minus 1. I'm presuming that equals n squared. Now I want to see what happens when I add the next number, when I go to the next number on the list. So the next odd number after 2n minus 1 is 2n plus 1, I'm adding that on. But this part over here is, by the inductive assumption, is equal to n squared. So I have n squared, bring down to 2n plus 1. Well, n squared plus 2n plus 1, anybody who knows that a factor knows that that's n plus 1 squared. And we did it. So we showed that if everything up to this point equals n squared, when I add the next number on, I get n plus 1 squared. And that is exactly what I wanted to show. And we know that, so if it works for n, if it works for n, it's going to work for n plus 1, but I know it works for 1. So for us, 1, it's going to work for 2, then 3, 4, 5, 6, 7, dot, 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 on forever. Let's look at the spreadsheet. Let's sort this out. So first way, again, I'm far from an expert on spreadsheets, that kind of stuff, but first we're going to do the, oops, that's not what I want. All right, see, this is just the n numbers. This is the numbers 1 through n. Now I want to look at the sums. So here I'm just going to put a 1, and here I'm going to say this is equal to this number here plus whatever's over there, and that's 3. And now, I don't think that's what I want. Oh, I just realized my brain is in the wrong place here. Let's just delete this whole thing and start over again. I'm sorry, I want the odd numbers. So I want this to equal to 2, 2, my brain just lapsed for a second, so forgive me. 2 times n minus 1. And that's all we want. And let's move it down like that. And pow. So we just want the odd numbers here. And now I want the sum. So I'm going to call that 1. And this is going to equal this, whatever's there, plus whatever's up there. And I get a 4. And now if I carry that pattern here, wow, look at that, perfect squares. I mean, you don't get more perfect than that. Whereas if I do n squared, I mean, this is a no-brainer now. This is equal to n squared. I mean, come on, we're talking no-brainer over here. Same numbers. I mean, exact same numbers, and they're all perfect squares. So we see that when I add 1 plus 3, so 1 just gives me 1, 1 plus 3 gives me 4, 1 plus 3 plus 5 gives me 9, 1 plus 3 plus 5 plus 7 gives me 16. These are all the same as the perfect squares, because this column here, the E column is the perfect square, is the square column. The C column is the sum of the odd numbers column, and the 2 columns match perfectly. So there you go. Now I'm going to get rid of this. I don't need it anymore. And you have it on tape. We don't need it anymore, and I'm going to go on to the next problem. So let me just dump this, discard it, and that was beautiful. Thing of beauty. Thing of beauty is a joy forever. Okay, let's go back to the textbook, and I want to do this guy right here. This is the sum of the squares of the natural numbers. So 1 squared, 2 squared, 3 squared, n squared. Well, you probably learned in calculus that when you do like Riemann sums, you probably learned the formula for this is n times n plus 1 times 2n plus 1 over 6. So let's just go through, let's see how we prove that. So where are we here? Let's go back to here. Okay. So what I want to show is that 1 squared plus 2 squared dot 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 plus n squared is equal to n times n plus 1 times 2n plus 1 over 6. It's a very famous formula. Step 1 shows it's true for n equals 1. So 1 squared is equal to 1 times 1 plus 1 times 2 plus 1 over 6. That's basically 1 times 2 times 3 divided by 6, which is indeed 1. Step 2 is I want to assume it's true for a certain value of n, show that once it's true for one value of n, it's going to be true for the next value. In order to be true for n, I want to establish that it is being true for n plus 1. So I'm adding the next case, the n plus 1 case. Now this first part over here, by the inductive assumption, the 1 through n, 1 squared through n squared, that's equal to n times n plus 1 times 2n plus 1 divided by 6. And now I'm going to get a common denominator here. So I have 6 over 6. And I'm combining the two fractions. The way I personally did is I pulled out a common factor of n plus 1, combined all the other factors. I wound up, crunched everything out. I wound up getting n plus 1 times 2n squared plus 7n plus 6. But that factors into n plus 2, 2n plus 3. But that is the next case. Because in the case of n equals n plus 1, so I have n plus 1, n plus 1 plus 1, 2 times n plus 1 plus 1. You get it? Because that's 2n plus 3. And it all works out beautifully. Let's take a look at this with our spreadsheet, just again, just for fun. So let's, why do I say just for fun? Because looking at the spreadsheet like I do for you, it doesn't prove it's right. I could have a spreadsheet and work it out for a million cases. But just because it works for a million cases doesn't mean it's going to work always. It's still possible that it couldn't work. But on the other hand, when you look at a lot of cases, it gives you a good feel for what's going on in it. And usually it's, usually if it works for so many cases, it usually is true, but just saying. Anyway, let's go to our little spreadsheet. So let's do the same. Let's do this step by step. 1, 2, 3, 4, 5, 6, 7. And now let's square everything. I'll look at some squares here. Let's get some squares. All right, so here we have squares. Now, what I want to do, I want to look at the sums. So the first column is just going for 1, that's how I'm doing it. The next column is going to equal this plus the previous. And following that along, we get this. All right. Now, this may not look like much to you, but let's go to the formula we had before. We had n times n plus 1 times 2n plus 1, 2 times n plus 1, and divided by 6. And blah blah blah. Anyone? Oh, I forgot. I think I forgot the little times thing. Okay. 2 times n plus 1 divided by 6. Let's try it. Okay, there we go. And so this is n times n plus 1 times 2n plus 1 divided by 6. And let's see what numbers we get when we run this thing. Now, what I really want, I'm hoping that the E column matches perfectly with the C column. That's what I'm hoping. And let's see if it works. Yeah, look at that. Look at that. Beautiful match. Every number is the same. Look at that. How? So we see that when I added 1 plus 4 is 5, 1 plus 4 plus 9 is 14, 1 plus 4 plus 9 plus 16 is 30, so on and so forth, but that matches with the column, this column, which is n times n plus 1 times 2n plus 1. So we see this actually does work. That is fabulous. Now, like I say, this is just something that makes you feel kind of good that it all worked out, but proof is really the use of the spreadsheet is not a proof. It's just me showing you how this stuff works out with actual numbers. So that, my friends, is the story, and we're ready to rock and roll. That's it for this little video. And our next video next video is going to be on 1.2, but we got time for that. Let's celebrate 1.1. Yay! I just celebrated 1.1. And that's kind of how you do a proof by induction. Anyway, I'm going to stop the video and I'm going to stop the video and we're going to see you guys next time. Bye.